Hello everyone, and lecture today we will continue the topic in angle and direction measurement. Basically, this lecture will have three contents: the direction measurement with a magnetic compass, the measurement of the horizontal angle with repetition, and the method of prolonging a line. First, let's see how we can use the magnetic compass to measure the directions of one line. Actually, the compass is widely applied for surveying. In the compass, there's the magnetic needle, which is always parallel to the magnetic meridians, and it will always point to the magnetic north. When we use the magnetic compass, we will try to align the south-north line to the line on the side, which is the direction we want to measure. And then the angle between the line on the side and the true magnetic north is the one we're going to use to determine the directions of the line on the side. In this example, you will see that the needle is pointing to a degree of 60, and it's actually between north and west. In that sense, we can actually read the true direction about the line on the side as north 60 degree east. Here we will do an interchange about the direction of west and east. If we have the needle pointing to some place between south and east, then that one could be read as south 40 degree west. Similarly, can be applied to the other regions. The direction measurement of compass is highly related to the magnetic north. However, on the Earth, the magnetic north is different from the true north. In general, the horizontal angle between the magnetic north and the true north is defined as the declination, and we have to correct declination for the direction measurement with compass. Generally, the magnetic declination varies at different locations of the Earth. We will usually record the isogonic chart to define the magnetic declinations at different locations. The figure here shows the distributions of the magnetic declination. In general, you can see that for the locations in Toronto or Hamilton area, the magnetic declination is around 12 to 16 degree. In addition, the magnetic declination is not constant at one location. Instead, it's changing over the time. And usually this kind of change can be measured with the secular variation, which will be the change in 300 days, or annual variation or daily variation. With these three variations, we are able to predict the declination over the time. Also, there's another type of the variation which is called the irregular variation, and it's usually caused by the sunspot. With that one, there will be some magnetic disturbance, and it will affect the accuracy of the direction measurement with compass. Now let's go through one example to see how we can correct declination for the direction measurement with compass. In this example, we assume that a magnetic azimuth of 54 degrees 30 minutes was observed for the line A to D in 1994, and the declination for the area was found from the isogonic chart in 1990, and the value is 17 degrees 30 minutes east, with an annual change of 3 minutes westwards. And it wants us to find out the true azimuth of the line A to D. Now let's see how we can solve this problem. First, we need to summarize all the assumptions in this problem. We are given the azimuth, which is the measured azimuth of the line AD as 54 degrees 30 minutes, and it's measured in the year of 1994. Also, we have the declination in 1990 as 17 degrees 30 minutes to the east, and the variation of the declination is 3 minutes per year. It wants us to find out the true azimuth of the line AD in 1994. First, for the solution, we need to draw the directions of the line with respect to the magnetic north and true north. This one shows the magnetic north, and we have the other directions east, south, and west. And we know that the azimuth of the line AD is 54 degrees 30 minutes. Now for the line A to D. This one comes from the definition of azimuth, which is the angle from the north to the target line. We also know that in 1990, the deflection angle from the true north to the magnetic north is 17 degrees 30 minutes, and the magnetic north is actually on the east side of the true north, which will give you the true north as the green line here. So we have the other three true directions, and the angle here is 17 degrees 30 minutes. We also know that the magnetic north is moving westward at every 3 minutes per year. Then in the solution, we can first check what's the changes about the declination from the 1990 to 1994. So the change of the declination is 3 minutes times 1994 minus 1990. That is 12 minutes. And as it's moving westward, so we have the declination in 1994 as the declination in 1990 minus the change of the declination, that is 17 degrees 30 minutes minus 12 minutes, which will give you the value as 17 degrees 18 minutes. And with that, we can find out the true azimuth of the line AD as the azimuth measured for the line AD in 1994. In this sense, we need to add the declination. So that is 54 degrees 30 minutes plus 17 degrees 18 minutes, which will give you the answer as 71 degrees 48 minutes. So that's the solution about the true azimuth of the line AD. Here is the second example about the correction of declination. Assuming that we have the magnetic bearing of 34 degrees 30 minutes northwest from the old surveying plane on August 20, 1910, and it's desired to re-establish this direction on the site in 1995. The isogonic chart in 1990 showed that the declination in that area is 20 degrees west. Also, we know that declination is moving eastward at 2 minutes every year. It wants us to find out the magnetic bearing that must be used to relocate to the direction of the line in the field. So for this problem, we need to first find out the true bearing of the line, and then convert it to the magnetic bearing in 1995. Now let's see how we can get the solution. First of all, we need to find out the declination at the 3 years mentioned in the problem, 1990, 1995, and 1910. We will put this declination in the directions of true north and south for the Earth. So let's first draw the true directions, north, south, east, and west. So this is the true direction. And we will first go to check the declination in 1990. In 1990, the declination is 20 degrees west, which would be the west side of the true north. And we will have the declination in 1990, as we show in the red line here. This is the magnetic north in 1990. The angle here is 20 degrees. We also know that the declination is moving eastward at 2 minutes per year. So we can anticipate that in 1910, the magnetic north will be on the west side of the north of 1990. So that is some place we're gonna show here. The angle here is the changes of the declination from 1910 to 1990. And we say this is a delta D1. We get a delta D1 is 2 minutes times the years from 1990 to 1910, which will give you the angle as 160 minutes. That is 2 degrees 40 minutes. With that, we can find out the declination in 1910 as the angle here, which is 20 degrees plus 2 degrees 40 minutes. That is 22 degrees 40 minutes. And next, we can find out the declination in 1995. As the declination is moving eastward, we can predict that in 1995, the magnetic north will be on the east side of the north in 1990. And the angle here is set as delta D2. So for delta D2, that is 2 minutes times the 5 years from 1990 to 1995. So that is 10 minutes. Also, we can find out the declination in 1995 as D1995. That is 20 degrees minus 10 minutes, which is 19 degrees 50 minutes. Moreover, we know that the angle of a line, say it's a line O to A, was observed as 34 degrees 30 minutes northwest, which would be on the west side of the magnetic north in 1910. And with that, we can find out the true bearing. For the line OA as 34 degrees 30 minutes plus the declination, that is 22 degrees 40 minutes in 1910. So that is 57 degree 10 minutes. Also is force in the northwest direction. And then we know that the angle here is 47 degree 10 minutes. We can find out the bearing of OA in 1995. That would be the true bearing minus the declination. Minus the declination is 19 degree 50 minutes, which will give you the result as 37 degree 20 minutes. So that's the answer we need to get for this problem. The second content that I want to introduce the horizontal angle measurement with repetition. We know that there exist some errors in the measurement, especially random error and systematic error. In order to minimize such error, we want to repeat the measurement for many times. The repetition is one efficient method to solve such issues. In general, with the repetition, we are able to increase the precision of the measurement, remove the systematic errors, and also decreasing the possibility of mistakes. For the horizontal angle, there's one standard procedure for the repetition. For example, if we want to measure the angle between two lines, OA and OB, the angle here is set as alpha. Then at first, we want to set up the instrument at point O. And then put the telescope and point to A. Initialize the reading as 0. Or we keep the original value. And then point to B. Get the first direct reading. That will be the first reading about the angle of alpha. And next we will log the reading and reverse the telescope. And then we will point the telescope to the point A again and continue the reading. And next step, we will move the telescope to the point B and get a reverse reading. And next, we will go back to the step 4 and repeat 4 to 6 for several times, which will be the times you defined for the experiment, and get a final reverse reading. We will then use this reading for the process of the angle measurement. The table here summarizes the result from the repetition experiment. In this experiment, we will try to measure the angle between two lines, FE and FG. So that will be the station where we place the instrument, and E is the initial line, G is for the final line. So we have the alpha here. And in this table, we will have 3 readings from the experiment. The first one is set as alpha 0, which will be the initial reading from the instrument. For most of the experiment, we need to do some initialization for the instrument, which means we want to set this value as 0 degree. If you haven't set the value, then you need to record the value. The second one is the first direct reading before we apply the repetition. And the last one is the reversed reading after the number of the repetition applied. In this experiment, we applied 6 times, say it's alpha 6, and the repetition is 6. Then we can use this information to find out the average angle we can measure from the experiment. At first, we need to find out the rough value of the angle from the direct reading. So in the first step, we get alpha equal to alpha 1 minus alpha 0, that is 216 degree 21 minutes 0 seconds minus 136 degree 1 minute and 50 seconds. The result is 80 degree 19 minutes and 10 seconds. And in the next step, we need to check the angles we turned for the instrument during the 6th repetition. So the total rough angle that we measured during the 10 repetition would be n times alpha, that is 6 times 80 degree 19 minutes 10 seconds, that is 481 degree 55 minutes 0 seconds, and it's higher than 360 degree. It indicates that we do the repetition and pass the origin, which is 0 degree once. That gives you the number of the pass as 1. With that, we can then calculate the average angle that we measured. Alpha bar equal to alpha 6 plus k times 360 degree minus alpha 0 over the number of repetition. In this case, alpha 6 is 257 degree 57 minutes 50 seconds plus 1 times 360 degree minus 136 degree 1 minute 50 seconds divided by 6, and will give you the average angle as 80 degree 19 minutes and 20 seconds. The value here is very similar to the value we get from the direct reading. But this one is the average value, which is more accurate and is able to eliminate some systematic errors and random errors. The last content we're going to learn is prolonging a line. This one is applied to extend a straight line to an undefined point on the ground. The point will be beyond the limit of the sighting distance or is invisible from the line. For example, if we're doing a construction about a straight freeway segment, say that the length is 10 kilometers. We will usually start with a short segment, say it's AB, which is around 100 meters, and then we want to extend this line to a point and make sure that A to P is 10 kilometer. And this process about finding the straight line, which is a BP aligned with the line AB, is called prolonging a line. There are many methods applied to prolong a line. The first method is a direct method, where we can apply the instrument directly to find out the extended line. For example, if we want to extend a line AB to the point P, then we can place the instrument, say in the satellite, at the point B, and we have on the back side to A and the foresight to C. Once we find out the intermediate point C, we will move the satellite to the point C and find out another point D, and eventually we'll find out the point P with the given distance. However, this system is not quite reliable. If there isn't any systematic error or random error, then the measured location will be very different from the true location. For example, at point B, if the instrument is not perfectly aligned, then the line of AB will not be aligned to the line BC in a straight line. In that sense, there will be a small distance between the true point C and the measured point. Say it's a delta XC. And then if you apply the satellite at point C, you will get another wrong location at point D. And the error here, delta XD, will actually be larger than delta XC. And if you repeat this process, eventually you can find out a very large error at point P. So in order to solve this issue, we introduced a double centering method. Well, at point B, we will not apply a single measurement. At first, we will apply backside to A and foresight to C as one measurement, and then we will reverse the telescope and complete another backside to A and foresight to C. With that, if there's any systematic error or the random error, then you will find out 2 points, C prime or C double prime, which will be placed at two sides of the location C. And then you connect C and C prime, find out the middle point, and this point will be closer to the true location of the point C. And at next step, you will put the instrument at point C and repeat the process to complete the direct measuring and the reversed measuring to get a D and D prime and find out the middle point as D. And the similar process will be repeated until reach the targeted location P. So that's the double centering method. In real world, sometimes the line of sight for the prolonging a line task is blocked by some objects. In that sense, it's impossible for us to apply the direct method or the double centering method. So we need to consider some other procedures to extend the line. The first one is called the perpendicular method, which is shown in the figure here. For example, if we want to extend a line AB to pass in the building, and the building will block the side of the line AB. In that sense, we will first find out a parallel line CD. CD is the same, the length of CD is the same to AB, In addition, we have AC is perpendicular to AP, and similarly BD is perpendicular to AB. And we want to find out in the line CD which will not have any objects block the site. And then we can extend the line CD with the direct method or the double centering method to find out the extended line EF. Once we have the EF passing the object, then we can find out a parallel line GH. Here we want the GH will have the same length to EF. Also, EG is perpendicular to EF, and FH is perpendicular to EF. In the meanwhile, we also want AC equal to BD equal to EG equal to FH. In that sense, we can guarantee that AB and GH are on the same line. The other method we can consider is angle method. For example, if the line AB is blocked by the tree on the pond, then we can consider introduce some angles to pass these objects. At first, we can extend the line AB to the point C with certain angle alpha. And then at point C, we will have the clear view, and we can then try to extend the BC with the reverse angle 2 alpha to the point D. Here we have to make sure that BC equal to CD. In that sense, D will be aligned to the straight line of AB. And then we will need to extend the CD to a point G with an angle alpha. And now we will get the line DG. DG will be on the same line of AB. And this will give us the choice to extend the line AB to pass the object between B and D. In this class, we will use a satellite to measure the angle and direction. The link here shows the operation of satellite. You can watch this video together with the third lab videos. It will be very helpful for you to understand the lecture and the lab experiment. So that will be all about lecture today. Thank you very much for your attention.